So in this video, we're going to try to develop conceptually L'Hopital's rule so we have a little bit of a sense or idea of where it comes from. So we're going to want to be taking limits of the form the limit as x goes to a of a ratio of two functions in cases where we have indeterminate forms. There's going to be a variety of indeterminate forms. These are the only two we've looked at so far, but there are a lot more. If you remember from Calc 1, you can, for a function f and g, come up with tangent line approximations for those functions. So what you want to recall is that the tangent line approximation for f of x, you get it by at a specific value, x equal to a. So you have to generate a tangent line approximation based at a specific value. And the way that we did that in Calculus 1 is we evaluated the function value at a, and then we found the derivative or rate of change at a, and then we multiplied the rate of change by delta x, where delta x is just x minus the number at which you've centered the tangent line approximation. So all this is right here is from Calc 1 the tangent line approximation of f of x, and this right here is just the tangent line approximation of g of x right here. And what we want to recognize is that the tangent line approximation of f of x and g of x will have exactly the same value that f of x and g of x have at x equal to a. So at x equal to a, what's true is that f of a equals the tangent line approximation of f at a, and g of a equals the tangent line approximation of g at a. If you can think about it this way, here's the tangent line approximation. What happens if you put a in? You get a minus a is 0, 0 times the derivative is 0, 0 plus f of a is f of a. So the idea is the tangent line approximation and the function have the same values, have the exact same value at the number about which you've centered the tangent line approximation, which means that the limit as x goes to a of the ratio of f of x and g of x will be exactly the same as the limit as x goes to a of the ratio of the tangent line approximations. And here are the tangent line approximations. You can kind of justify that this is true also just thinking about it graphically. If I have a ratio of two functions, so over here I've got the two functions in my ratio f of x over g of x, it's f of x over g of x. So if you look at the tangent line approximation, which I have here in red for each of those two functions, and I did my tangent line approximations at 4, at x equal to 4. So if you look at them, the function value and the tangent line approximation value are identical at the number at which I centered my tangent line approximation. So it should be clear that at a, or in this particular example at 4, they have the same value. The ratio of the functions and the ratio of the tangent line approximations will be the same. So you can kind of start to justify or come up with L'Hopital's rule. So let's consider what the case when we have the indeterminate form 0 over 0. Well, if we have the form 0 over 0, that means that f of a is 0 and g of a is 0 if our form is 0 over 0. So let's play with this a little bit. So if the limit as x goes to a of the ratio of f and g is the same as the limit as x goes to a of the ratio of the tangent line approximation of f over the tangent line approximation of g, we can sub in those two tangent line approximations. And in the case where we have the indeterminate form 0 over 0, f of a is just going to be equal to 0 and g of a is just going to be equal to 0. So it's going to simplify like this. And then when we add 0 plus this, we're just going to get f prime of x times x minus a over g prime of x times x minus a. But x minus a divided by x minus a is going to be equal to 1. And so what we get is that the limit as x goes to a of the ratio of the functions is the same as the limit as x goes to a of the ratio of the function's derivatives. And this is L'Hopital's rule, justified for or derived for the case where we have the indeterminate form 0 over 0. Another way to get at this is to use the mean value theorem or the extended mean value theorem, which is also a theorem that you looked at last semester in Calc 1. So it doesn't justify it for the case infinity over infinity or the other indeterminate cases, so that should be something that you spend some time thinking about. But it does justify or come up with a formula for the case where we have the indeterminate form 0 over 0. So we're going to formalize this, and this would be what you would want to put in your notes primarily, because this is the tool that you're going to be using in the current homework assignment. So L'Hopital's rule, not Hospital's rule, L'Hopital's rule says that, hey, if you've got f of x and g of x and their derivatives exist on some open interval that contains a, and f of a over g of a is any one of a bunch of indeterminate forms that can happen, then the limit as x goes to a of the ratio of the functions is the same as the limit as x goes to a of the ratio of their derivatives. So the only other thing I would comment on about this is, notice we're not taking the quotient rule. This isn't the quotient rule, right? We're not doing f over g and then taking the derivative of f over g and getting, hey, that's going to be the derivative of the numerator times the denominator minus the numerator times the derivative over the denominator over the square of the. It's not the quotient rule. This is just saying, hey, just take the derivative of f, take the derivative of g, get that ratio, and the idea is this ratio might be a ratio for which you can find the limit more easily than you can find the limit for the original ratio. So that's the idea behind L'Hopital's rule.